So there are a couple of other issues related to alligatory variability that we are looking at in this project. These relate to two issues that have been brought up along the way. One is the shape of the distribution in the upper tail, with basically deviations from the standard assumption of log normal over the entire distribution range. And the second one is the potential effects of spatial correlation in the data that would affect our global estimates of phi and tau from data sets that have not accounted for spatial correlation. We went briefly into this subject in January, basically looking at the residuals from ground motions from the various, Norm presented this in terms of the residuals from his data set, in terms of both the within event residuals and the event-to-event residuals. What came, looking at this example, is that we see from the intra-event or within-event residuals, on the right here, we have what is called a QQ plot, which basically compares the quantiles of a fitted of the distribution fitted to the data. So basically, a theoretical quantiles from a fitted distribution, in this case log normal, to the actual quantiles of the data, the actual residuals of the data. And the departures from a one-to-one line indicate deviations from the assumed model. And in particular, if you're at the upper quantiles and the deviation is up above the line, that implies a fatter-tailed or heavier-tailed distribution where the basically higher probability of extreme events provided by the assumed distribution. So we see from this plot that we indeed have deviations upward in the heavy-tailed direction above the line at the higher quantiles. The dashed lines on here are from the fitting program in R, which basically are bootstrap confidence intervals on what the quantiles could be from the sample size. So the bootstrap data show that you would expect, or you could see statistically some variation away from a one-to-one line, especially as you get to the edges of the data, but that the residuals themselves are at least deviating a stronger portion than the statistical uncertainty at those tails. So this is the result showed for PGA. We see the same at longer periods. These are, again, residuals from the ASK model at 5 hertz and at 2 hertz and 1 hertz. And looking at I've looked at the CY14 residuals, and I see very similar things. We do not see the same deviation in the tau, the event-to-event residuals, but we also have much fewer data points to look at. We're looking here at thousands of data points. This is a distribution of, at least at PGA, is probably 4,000 or 5,000 data points, whereas for tau we're looking at 150 to 200 event terms. So it's much more difficult to see whether this behavior occurs in tau. But it's clearly appearing in phi, this is ergodic phi. And now I took Linda sent me the residuals from the phi S to S, or single station phi SS, and we also see heavy tails in that distribution. We were hoping that maybe they were showing up in the phi S to S and would not be a phi SS issue, but they're there in basically the same sort of shape. So this is both the magnitude dependent or magnitude independent values of phi SS at PGA, and if we look at 1 second, we see similar effects, basically some trend to a heavier tail at the upper end. So how can we represent this or deal with this in our actual calculations? And one approach to this is to use what is termed a mixture model, where the distribution of residuals is represented by a weighted mixture of say, 2 normal distributions, one with a larger variance and one with a smaller variance. Basically, then you use that to calculate the probability of values over the entire distribution range. Another approach which has been suggested is to use an alternative distributional form for the upper tail, such as a power law distribution. So this is an example of using the mixture model approach, where I've taken the plot on the left was the plot from Norm's the ASK intra-event residuals for PGA, and just the same plot repeated here. And on the right is fitting those residuals as a mixture of two log normal distributions, one with a standard deviation about 10% higher, one with a standard deviation about 20% lower. And you can see that when you use that type of form, that the resulting QQ plot, or comparison of the empirical residuals with the theoretical model residuals, now comes much closer to the one-to-one line, at least in the upper tail, which is where we're mostly interested, and we're not too worried about deviations down here at very small ground motion levels. So the mixture model worked well for at least in representing the distributional shape for the ergodic residuals for phi. And also this is a plot for the phi S residuals for the magnitude dependent model. Again, on the left was the plot originally with just a single normal distribution, and on the right is a mixture model with basically two distributions, one with about 20% larger sigma and one about 20% lower, and about an equal mixture of those two models.
Bob, is this just from trial and error, or is it a regression or estimate to get these?
It's the fit?
Yeah.
The fit is done by expectation maximization and a code in R.
So R does this for you?
R does this for you.
Okay.
So it's basically a cluster model fitting process. Tom.
Could you be a little bit more specific about how you mix? You just take two log normally distributed data sets and...
No, it takes the data set and looks for a mixture of normals that would match the observed distribution of the residuals.
So, I mean, if you take two Gaussian processes and combine them by multiplying them, you
You don't
convolve
multiply,
them.
you sum them. They're weighted. Basically, you take two density functions with weights, and you sum them together to get the composite density function.
So if you did that to log normal things, you would not end up with a normal distribution. But if you did it to
the
normal distributions, you'd end up
Yeah,
with
so
a
these
normal.
are done on the log residuals.
So you're doing a linear sum on logarithmic.
On the
On log
residuals
normal.
aren't in log space, yes.
I see. So it's some kind of mixed mode, but you're in both log space and in linear space. Is that?
No, well, it's all done. All the operations are done on the residuals in log space. So we basically do everything in log space and assume a normal distribution.
Yeah, I'm trying to think physically. So when we do something we call log normal, we're assuming we have a large number of uncertain processes that are multiplied together to give a final output.
Right.
And central limit theorem says that's a log normal distribution. If we had many uncertain processes and added them together, then the answer would be a normal distribution. And you're using two things that we're adding two processes together, and we're assuming those two processes are log normal.
No, I'm doing it all in log space. So I'm
So
So I
adding
think
is multiplying.
They're
Right?
all
Adding in log
multiplicative.
space is multiplying.
So if you multiply two uncertain normal distributions together, it gives a normal distribution. That's a fundamental theorem. I
No,
mean.
if you're in log space and you have basically a density function which is now normal. On the log residuals, if a parameter is log normally distributed, that in the log of that parameter is normally distributed.
That's right.
Okay, so I'm in a normal distribution, Instead, I'm saying instead of the process being a single normal distribution, it's a mixture of two normal distributions, where one of them has got a broader uncertainty than the other one.
Yeah, so, but when you say mix them, that's where I'm having trouble. If you mix them,
The mix is a sum of two density functions in log space.
So what comes out is not normal anymore.
It's no longer normal. It's
Forget the log, just take the two normal distributions, sum them up. It happens so that the data is log, right? That's the same thing. What?
no.
Maybe just to clarify the confusion, if you add two normal variables, you convolve the PDFs. So this is not adding two normal variables. It's simply a trick. It's averaging the PDFs. It's not convolving them.
It's
It's
averaging two density functions.
It's not average, it's not adding two samples together to make a new distribution, if that's what you mean. Just as Bob said, he adds the density functions. You have two
Tom,
different
the
shapes,
mic's
they're
right
going
there.
to get a shape that's not normal anymore.
Yes.
So could you give a physical example of how this would happen?
A physical example? That the physical example is that we have two processes in the population, one with greater variance than the other. And we have a mixture of those populations in our set.
Another, well, maybe not
That's-
entirely physical example would be if you had used the power law transformation. That's a case where your input is normal and your output is slightly non-normal. That will lead you to this to something of this kind. Because if you have power law transformation, some circuit that is not quite linear, and you give it a normal input, and the output will be this slightly deformed shape, which matches your shape here.
I think Bob's explanation is the easier one to follow. There's two processes going on. We don't know
That's
how
right,
to separate the
That's right.
two. And so we're going to say what we've got in our observations is a mixture of two processes that we can't model by a single normal distribution. And I'm going to try to back it out into the two underlying processes. You could have 50%, or it could have been 30% one process, 80,
Yeah.
70% the other, and so
That's good. I agree.
And the process of use of fitting looks for how many mixtures might be in here, and for these cases, it's typically showing that there's a mixture of two. That's the optimum fit from the algorithm. It's a mixture of two distributions, with one with about 20% higher variance and one with about 20% lower. At least in my initial exploration of this process. They have about the same mean. I'm working on getting them to have the same mean, but they have about, the difference in the means is actually pretty small compared to the standard deviations.
I'm sorry, maybe I'm just being thick, but when we don't mix things, we read one value, which is the sum of different kinds of,
No, but
or the multiplication of different kinds of uncertain things. I mean, if we took a bunch of green balls and red balls, they may have different kinds of distributions, and we'd have a mix of green and red balls, but that's not what we're doing. We're coming up with one peak acceleration or something like
we
that.
have one peak acceleration from one earthquake at one site, and we have another peak acceleration from another earthquake at another site. And we are putting all of those together into a composite distribution, which we traditionally is treated as log normal. And what this is suggesting is that we have a fatter tail than a constant log normal over the entire, all that data over the entire span is not fitting by a single log normal distribution.
I see.
It's fit by a mixture of log normals, one with a larger sigma and one with a smaller sigma. And
see.
that could be used to mimic the observed fatter tail that we see, assuming a single sigma over the entire, for the entire population.
All right, I've got it now. Thank you.
John?
So if I understand correctly, what you're doing is you calculate first the sigma in the customary way, then you reduce it by factor 0.8, increase it by the factor 1.2, go through this process of convolving the two together, and you're playing around with those factors, the 1.2,
Yeah,
the 0.8.
the
You try
code programs are, yes.
You try many combinations.
Yes, the expectation maximization algorithm in R does all that for me.
So it's doing that internally.
It's doing it, yes. Basically, it's finding the optimum mixture to represent the distribution it sees in the residuals as a mixture of normals.
And it's always combining two distributions
No,
of the
it
same
looks
type.
across whether it can do 2 or 3 or 4 or 5. It searches across how many mixtures there may be. And this is the solution that comes out of this run is that it's best fit by a mixture of 2 normals.
Does it ever consider, say, a normal with another type of distribution?
That would require a different set of, right now it's just mixtures of normals.
Okay.
I mean, you can certainly there are mixtures of, you can mix anything you want.
So the
Whether you
more
wanna drink it or not,
distributions
I
you
don't know.
combine, the better fits you get, but you get a point of diminishing returns.
Yes, it
right.
basically, I mean, it does search across whether it could be 3 or 4 or 5. You can consider this as like a discriminant analysis, where you're looking for clusters of information in 2D. It's basically a 1D cluster analysis, looking for what would represent the model. And what comes out is that these residuals are well represented by 2 normals with means essentially 0, essentially the same mean, but one sigma bigger by about 20% and one sigma smaller than the sigma you would get from just putting them all together.
Then, I think Norm either today or yesterday mentioned that you are going to ignore one of them.
But I can't hear what you're saying.
Sorry?
I can't hear what you're saying.
Norm mentioned, I don't know, it was today or yesterday, I said you can only take care of one of them. I was curious if
Our
you
current logic tree doesn't have a branch to say it's log normal all the way, or it's a mixture model. And what we're saying is if all of our analyses or data sets are showing a fat tail, why are we bringing along a regular tail, right? So that you could just say, this is the model, okay, and we get there. Now, do we need to run uncertainty in that or not? Depends on how much this drives the answer. So all of these things, we want to capture them, and we want to get uncertainty in the important parameters so that we capture uncertainty in parameters that are having a marginal effect on the final result. Then we won't want to add the complexity, right? But we really should have had a branch of log normal versus mixture model, and that's what Linda put up. That was the right way to set up the problem. But we could decide it's so strong to favor the mixture model that once it gets a weight of 0.9, it's effectively 1. Let's make our life easier.
Tom?
So for these high accelerations in the fat tails, I mean, at least some significant portion of them are these asymmetric records that are clearly a different class of record than almost all the other things in there. I mean, they can't be linear dynamics. There's sort of a theorem in linear dynamics that says they're symmetric about 0. And in that sense, I mean, you wouldn't even begin to expect a normal distribution could explain that type of phenomenon. And that would be in the high frequency accelerations. When we go to the low frequencies, and we're talking about maximum low frequencies, I'm not sure why we'd expect a normal distribution there either, since everything we see about earthquake scaling of amplitudes of slip suggests power laws. So I don't know what the high frequency guy with the asymmetric looks like, whether it's a power law or not, but certainly the low frequency, you wouldn't expect it to be a normal distribution. In the high frequency,
But Tom, you're saying, I think, exactly what we're trying to accommodate. That is, at these very high accelerations, It's a different process.
Sure, but
Okay,
to
so
give
then
it
we
an-
need a mixture model to have those two different processes
So,
captured.
as long as you're mixing normal distributions, you'll get more width in the tail, but once you go very far out in the distribution, it's still a normal distribution, I mean. So, power laws are,
We're out to 4 standard deviations right there, right? That 4 means we're out at 4 standard deviations. That's pretty far into the tail.
so how far do you need to go?
4.
We get almost no contribution beyond 4 standard deviations to even at 10 to the minus 6, 10 to the minus 7. Because at that point, you're controlled by more frequent events. I don't know almost any cases where we've had the dominant contribution above 4. So above 3 or above 2 here, where you can see this thing getting fatter, yes, then it's going to make a difference in the ground motion model.
Well, maybe you should try a power law as well.
There it is. You asked, and it's
Sorry.
on the next slide.
I just want to clarify something. The mixture of two normal distributions is not a normal distribution anymore, and you can approximate any distribution with a sufficient number of normal distributions.
Initial experimentation indicates that, at least in the data I've looked at so far, that we can approximate the shape of the distribution fairly well by a mixture of in log space of 2 normals with sigma ratios of about plus or minus 20%, and the mixture is about equal. Yes.
Bob, have you looked at, rather than trying to do the mixture models and mixing them, look at separate, like an extreme value model rather than a normal value for the tails? I mean, this phenomena is seen in other, it's seen in fracture dynamics and seen in a lot of other, it's observed in a lot of other phenomena. So, and they separate them out, like with a Pareto distribution at the tail, and preserve the normal distribution. Okay.
So another distribution that's been suggested is that we look at a power law distribution form, such as the Pareto distribution. So I've done a very initial trial to see whether that one produces, a somewhat large, significant, well, I don't know, I wouldn't want to use the word significant, a major difference in the results. Or can we represent the effect of that distribution by a mixture of normals? Which the reason that we would like to perhaps use a mixture of normals is that it's already easily coded into our PSHA software. So if we can do a mixture of normals and adequately represent the upper tails, then that would be, in terms of practical application, would be, I think, a reasonable solution. So I did a very preliminary an evaluation where I took the upper tail, basically the upper half of the residuals, and fit that with a Pareto power law distribution shown here on the right. So it does a reasonable fit to the residuals on the positive half of the tail. And then I computed the percentiles of that distribution down here, the lower table, just basically the 99th percentile, the 999, and the 999, basically out to 10 to the minus 2, 3, and 4. And how far out in the tail was I in the mixture versus how far out in the tail was I in the Pareto distribution, and the numbers were very comparable. So I think we can represent, at least in this range, the extreme excursions into the outer tails and on the range of 4 sigmas, and capture the proper probability levels with a mixture of normals in log space. But that's initial evaluation, and we have to of course, do more, and I have to move to longer periods to see whether that's going to work at longer periods. But at the higher frequency, it seems to be working reasonably well in terms of what we need to do to calculate hazard at the levels of interest. So that's what I have at this point on. Oh, one more slide. So any more Yes, Bob.
This is all to enable you to proceed with the rest of the analysis. You don't have to assign a physical meaning to that distribution or the set of them, although Norm's explanation makes sort of physical intuition sense that they're two different processes, but you don't have to know that even to proceed, because all you're going to do is take that and run with it for the rest of it. Do I have that right?
Yes and no.
Huh?
Yeah. Yes, we don't have to have it, but we would sure like to
No,
do
no,
that
I
instead
know
of-
you'd like to.
yeah.
And if you didn't have a plausible explanation for the two distributions, you'd feel very unsettled. But you have one that you think is plausible, that they're really a mixture of two data sets whose physical processes produce these different residuals. Is that right?
Yes.
So
Yes.
if that's right, do you have a feeling for an explanation for why one would be, 20% or even 30% higher out there?
Tom's got.
It doesn't bother me because you're going
Yeah,
to run with it.
I
but-
think, no, we don't have a breakdown to say, here's why this one is 20% higher and here's why it's 20% lower, and what is it actually trying to.
Yeah, and the other thing that I'm not going to say troubled me, it sort of would have surprised me, is why the centers line up so well, as apparently they do, or as, at least Bob Young said they did.
The middle of the distribution, you mean?
Yeah.
It's where it's really tight along the one-to-one line.
Yeah.
It's really close to log normal on these data sets. And that's because it's products of factors. That's
Well,
what
that-
Tom
so-
was talking about.
So that the center of that distribution is going to line up willy-nilly because it's a product of a bunch of factors,
Right.
and that's how we get log normals.
Yes.
Okay, and so then your physical intuition is that out there's some other process which is
Starting to go on,
okay.
right.
Or add into the process, or multiply into the process. Tom? Oh,
So this crazy slapdown phase, these asymmetric acceleration records, if in fact they are actually slapped down, which we don't know for sure, but they kind of look like what was slapped down seen in the nuclear test industry. The interpretation was quite clear in the nuclear test industry from down-hole measurements that the upper layers of soils, or whatever you want to call it, had actually been thrown into the air and went into free fall, and the high accelerations occur when the material recontacted the earth. So, and you might think, well, it's impossible, but if you go to various observations of things like the great earthquakes in India, clearly things have been thrown significant distances up to several meters through the air from one place to another. And at that point, if you ask how much acceleration could you experience when it recontacted, the answer is how far did you throw it? What was the trajectory of the system? And up to this point in time, we've seen these asymmetric things that have taken us up to 3.5 G, but it's really tough to put some sort of limit on those numbers from a physical point of view. So at this point, when we look at those records, I think to just fit a statistical distribution and say, now we've characterized the physics of what's going on, I doubt that. I think we probably need to know something about that physics if we really want to understand that problem.
On a slightly more reassuring note, my student just did the similar computation looking at tails using crustal Japanese data, the entire KickNet up to 2011 data set, and we get very similar tails. They start to deviate at about 2.5, an epsilon of 2.5. So it's similar to what's observed with NGA data.
Let's get to your last, you have 5 minutes, so let's get to your last slide.
Can I just offer a possible explanation as to why we are seeing this heavier tail? Because our database is basically a mixture of data from different regions, from different sites and different earthquakes. And now we are assuming they're all having the same standard deviation. But in fact, there may be some region may have a fatter tail, and some region may have a narrow tail. Right? And some earthquake may have a larger fee, some earthquake may have a smaller fee. So when you mix them all together, you're going to see at the tail the contribution from those, those mixture that has unusual distribution. I don't know if that's making sense or not, but
I think what you're saying is we could break the data set down and find subsets of constant standard deviation and then show how those are added back up to make this kind of a shape, right? That's as opposed to having R pull out 2 of the models, do it more on, let's say, on a region basis or something like that. Okay.
I think, you know, if you could ever get enough recordings at a single station, what Brian just said, you should be able to, you know, unless it's earthquake specific, but if it's sort of a mixture of stations or whatever, then maybe you wouldn't get the fat tail if you
Yes,
just
but-
looked at a single
But
station.
we need 10,000 recordings at
Yes.
that
Well,
station
maybe
now.
not that many.
To
but-
get
Okay,
out
at
to where we
5,000,
are.
To look out at 4 sigma.
Well, to get the .9999,
To get out,
okay.
to get out to this tail, there are 5,000 residuals in here.
What I said is hypothetical, not,
Yes.
not something I
So this-
expected you to
yes,
do.
What we are trying to do is do a better job in estimating the probability of extreme ground motions than assuming log normal with, possibly than assuming log normal with a constant sigma over the entire range. Whether it's magnitude dependent or magnitude independent, that's still, I mean, we see it in both cases. So the tails are indicating a deviation from a constant log normal distribution over the range. And we can do a better job of representing that by a mixture of 2 normals than by using a single normal. So I think that's, I mean, as a proponent at this point, that's what I would say is we could do a better job up here with the mixture of 2 normals than by using a single normal, which people have questioned, and now we're getting to the point where we have data that
But it's more than that, is that you would also say this mimics the power law model of the same phenomenon.
And it appears
right?
we can perhaps represent the power law behavior up there, at least adequately in the number of standard deviations we need to go for what we're doing. Whether we can get to 10 to the minus 10 with this is another question. So the final issue, the second issue we had to deal with or looking at is the effect of spatial correlation. In our, this was brought up by Jack Baker in some meeting or in his feedback, I guess, to us after workshop 2. And basically in our evaluation, we are considering, we do deal with co-located sites or very closely located sites. I think all the developers made some evaluation of what they should do if we have 3 or 4 stations within, a few tens of meters of each other. But he's talking more about spatial correlation over the range of multiple kilometers, and arguing that there is spatial correlation in the data and that it affects the estimate that these residuals should not be treated necessarily as completely independent in the way that we've been doing in the past. And so they've done an initial evaluation of the CY14 residuals, looking for the effects of spatial correlation in the residuals. And they see little effect when they input a spatial correlation model into the residuals. They see little effect on the estimates of tau and phi for frequencies, for the higher frequencies, less than 0.3 seconds or above 3 hertz. at the smaller magnitude range for, basically, Cho and Young's have a tau and phi 1, which are estimated at magnitudes around 5, and then the tau and phi 2, which is 6.5 and larger. They see very minor effect at longer periods for the smaller magnitudes. But at the larger magnitudes, tau 2 and 3, they see some effects in the spatial correlation, basically a reduction in tau and an increase in phi, such that the total sigma is about 10 to 20% higher. The total ergodic sigma in that frequency range is about 10 to 20%. So we need to explore this with other sets of residuals to see what we need to do in terms of mapping that into our final sigma model. Gabriel.
If you're using single station sigma, won't this variation map into VSS and go into VSS as opposed to going into tau?
Well, tau goes down.
Sorry,
Tau goes down.
tau is down and okay.
Phi goes up and tau goes down is what they're finding.
Okay. But doesn't it go into VS2S as into a side property? Well, no, but it goes, let me think.
I'm not sure what
Some
you're
other
asking.
earthquake, some other earthquake may sample a different subset of sites.
It's really, we haven't thought of this as site, it's really just close stations that are a couple kilometers apart are going to have a correlated amplitude, okay?
Okay.
Because
So
now
that-
they're
yeah, that
somewhat in the
reduces
same
tau,
path
okay.
direction and so forth.
Okay.
As you get far enough apart, we think they're independent, but that far enough is not 1 or 2
It's not
kilometers.
it's not tens of meters, it's kilometers.
and tens of kilometers maybe
Tens of
before you're down to
kilometers.
0 correlation. So
Okay.
when we just treat them as independent and ignore that correlation, we will underestimate the standard deviation, and that's what he's saying.
Okay, okay, that makes sense.
And Jack supposedly will be here tomorrow, so,
Yeah, so-
we can grill him in detail. Sigma total would be 10 to 20% higher.
So I can see
John.
why phi would go up when you consider these correlations. I don't understand why tau would go down.
We will have to ask Jack, it has to do with basically how much data you actually have, I think.
Part of the correlation you have of records within an event is captured in the event term. I think that's what Ken was about to
Right.
say, right?
So if the event terms are being scaled by what conceptually what the average residual is, and if a lot of the data are correlated, then that one residual, the 50 residuals are actually only really 20 residuals conceptually. And so it's not going to pull the mean as much in that direction. So that would potentially reduce tau. Because basically you're reducing the sample size in that area from however many stations you had down to the effective sample size due to the spatial correlation. So with that great answer, I have time to stop.
You're out of time, so thank you, Bob. Linda.